Good morning, I'm Giovanni Trezza and I'm a third-year PhD student. In this short video, I'm presenting my research activity about applications of machine learning on superconductors and solar fuels. Superconductors are compounds showing no resistivity when cooled below a critical temperature, and due to this fundamental property are employable in many fields. Motivation of this work lies in the fact that desirable superconductors have a high critical temperature and good mechanical properties, but current studies are based mainly on expensive experiments or high-burden simulations. The aim of this work, conducted in collaboration with the EPFL, is to train a proper machine learning model for the prediction of simulated superconductivity. To this end, I took advantage of around 700 crystallographic files of materials together with the calculated Eliashberg function, which properly integrated gives the two electron phonon coupling parameters lambda and omega log, and finally the critical temperature. From the practical standpoint, as model architecture, I used an equivariant graph neural network, which, by incorporating structure symmetries, enhances data efficiency if compared to traditional machine learning. I thus predicted the alpha square Fs, which once integrated leads to a reasonable prediction of an omega log, but a noisy prediction on lambda, which is in line with other works in the literature and still represents an open problem. During this year, I also collaborated remotely with the University of Cambridge, UK, on the Bayesian optimization for optimally orchestrating solar fuel generation experiments. Employing such techniques, we aimed to minimize the number of costly experiments towards the maximization of a proper objective function depending on 5 variables and related to the carbon monoxide production by means of photocatalytic micelles. Effectively, over the experiments, the objective function increases, together with other metrics. Indeed, the highest objective function sample, the holistic optimum, has for instance a CO yield which is nearly 4 times higher than the original one. Also, I used the collected data for training, validating and testing multiple machine learning models, predicting figures of merit of interest, and for ranking the primitive variables such models were trained on. In particular, the buffer appears always to be the most relevant feature. Leveraging a recent methodology we introduced based on a genetic algorithm, I also proposed alternative parameter combinations to achieve comparable performance by employing a lower amount of the most expensive components, properly rebalancing the others. In this particular case, we saved 30% of catalyst and 7% of photosensitizer.